welcome to another video. Today we're going to be talking about the correctness of the definition of the surface area measure. I've taken the liberty of writing the measure beforehand, so let's have a look. So we say that if phi of u is some simple k surface where phi is some k chart defined on some set u, which is a subset of the real space, then we define this surface area measure of some set B, which is a n-dimensional Borel set living somewhere on the surface S, which is precisely what this means. This is equal to the integral over the set of the pre-image of B under phi of this baby right here with respect to the k-dimensional Lebesgue measure. We note that we have a shorthand for the integral. We can simply call it jk phi of u. Alright, well, what do you mean by the proof of correctness? We wish to show that the value of the surface area measure of some set is independent of the choice of the map with which we choose to characterize the surface, so long as both of these charts map the whole surface. It is possible to do so because we only consider simple surfaces. So long as we have any two charts which map the whole surface, the surface area measure will be independent of their choice. Now, how do we prove this? Well, we begin exactly as one might expect. So let phi be mapping some set u into the n-dimensional real space, and psi mapping some v set into the n-dimensional real space B to k charts. Now, phi of u is equal to psi of v, which is equal to our surface S. This is the sort of equivalence I was talking about earlier. Now, observe that psi after phi is a map which maps the u set into the v set, and it is a homeomorphism. Why is it important? Well, because soon we will be taking the Jacobian of this thing, and we wish to make sure that it is differentiable, which, it being a homeomorphism, well, it doesn't really matter that much. It is a homeomorphism, but more importantly, it is a composition of two maps which themselves are differentiable, and ergo it is differentiable itself, and as such we can afford to take it Jacobian. Now, but it's also good to know it's a homeomorphism. Now, if we take the integral over the pre-image of B under psi over jk, that's our shorthand up here, psi of v with respect to v, using the substitution theorem from measure theory, we obtain that this is the pre-image of B. We are just copying it. Copy the integrand so far, but times the absolute value of the determinant of the Jacobian of psi inverse after phi with respect to u. Alright, but we have seen this before, actually. We have seen it in the change of parameters on a surface theorem or something like this, and thence we know that this is actually equal to the integral over the pre-image of psi of B of, again, we copy this, jk, well, I would copy this, of jk psi of V times the determinant of, and now we have lowercase d, isomorphism notation, of psi of V composed with, again, lowercase d, of phi of u. And here we have inverse, of course. Right. Well, that's all right and dandy, but why do we do this? Well, because we also know, so I'm going to put this in a little box here as a fact. Our shorthand of some function phi at u is actually always equal to the determinant of our little isomorphism notation of that function at that point. And this will be useful. So using this trick, we transform the first factor in the integrand. So we put this equal to the preimage of b under psi. Now we have the determinant of d phi u times the absolute value of the determinant. We split it. The absolute value of the determinant of the inverse psi of v times the determinant d, of course, of the determinant of d phi of u. Alright, well, but this is nothing less than the integral of the preimage of b under psi. Now the integrand will be simply, well, the determinant of phi under u. Oh, I forgot to mention that since we use the substitution theorem, we are of course now integrating with respect to u. How is that? Well, because I'm going to put another little box down here. We know that phi can be expressed as psi composed with psi inverse composed with phi. And if we take the determinant of both sides, we get that the determinant, or rather, rather, if we supplied it with these, so it perfectly matches our situation, we took the determinant of both sides, we get the determinant of d phi equal to the determinant of d psi times the determinant of psi inverse times the determinant of d phi. And this could be of just some positive numbers, and if we are not dealing with positive numbers, we could simply make them positive by adding the absolute value. But be it in either case, this matches perfectly or nearly perfectly our situation. So using exactly this sort of backward deduction, we arrive at this identity here. And by the first box I drew, we know that this is equal to the integral of the preimage of b under psi of j k phi of u. Voila, we get from here to here, and we have just demonstrated the invariance, or the sort of invariance we wanted, or we had set out to do in the beginning, and this concludes the proof.